Hi friends, myself Harshit Srivastava, your course instructor. Here in this series of lectures and practical exercises, you are about to learn and master the trending and stable NoSQL database IBM Cloudent, which is based on a popular CouchDB uh, with great enhancements to it. It is offered on IBM Cloud, bluemix platform where you can leverage a wide range of services in different categories like storage, mobile, web, analysis, DevOps, other categories as well, and develop an integrated solution with IBM Bluemix. Cloudit has enormous power and is scalable. That you will realize soon after watching first four lectures and being proficient enough to implement in your own project or your application just on completion of this course. So let's start with Cloudent. So first thing first, IBM Cloudent is a NoSQL database as a service. It is fully managed document database which consists of files or data stored in formats of JSON, JavaScript object notation. Uh, it has maintained a data access and availability at extreme scale. Uh, all uptime, no low time. Data is being available all the time. We will be learning CAP theorem to understand it in a better way. It has optimized for data availability throughout the regions, the durability, mobility, if you want to move from one location to other, and perfect for fastest growing mobile and web apps. It is well suited for scalable applications, whether it being mobile, web, IoT, and any kind of applications. It is compatible with Apache CouchDB, which has core storage engine and accessible through HTTPS API for web, mobile, IoT, and other applications. Let's learn a little about its history. It was founded back in 2008 by MIT researchers to solve the big data problem of Large Hadron Collider, which is located in Geneva, CERN, which is to experiment the particle accelerator, the other things where subatomic particles are being collided with each other to generate various cosmological or uh, subatomic quantum level experiments, uh, which has to be controlled by certain sort of supercomputers, and it has various problems. To address those problems, uh, no existing database at that time were prevalent enough to implement that logic. So MIT researchers decided to implement a new database based on CouchDB so that to perform certain steps. We are going to learn about CouchDB in the coming videos. Uh, it is born in the cloud, so it is one of the first generations of databases that is born on the cloud. The cloud has emerged before the cloud end has been born, before its birth. So it is designed basically in kept in mind about the cloud. So it has scalability options at its core. It is based on a CouchDB project and open source and the Big Couch project. As you have seen in the world map, there are various data centers of IBM Bluemix located across the world. Here are a few. We have more locations, and you can sustain your cloud and database among any of these locations or in a multiple of locations. You can store database data or create copies, replicas, and other things across different locations to suit your customer base or other business implementations. So here is a question basically why we should use Cloudin. There are plenty of NoSQL or other databases out there. So why you should use Cloudin? There are certain advantages and disadvantages associated with each kind of databases, as with everything else in this life. Um, the Cloudent is a NoSQL database, so it is very scalable, easy to manage, have JSON and other things. It is different from other NoSQL databases because it prevents the popularity crash due to traffic. And when traffic or number of users increase over a certain database, uh, after the scale of millions or thousands, uh, almost every database in relational category and other categories as well could not offer services over a range of users. Cloudent is a solution to that problem. It can handle any number of traffic. It could scale up very easily. The scalability, it has a cluster support. It is being implemented using cluster of various systems throughout the world or throughout data centers. It is easy to manage and integrate with other applications as it is available on cloud. As an application, you can create an instance by sitting anywhere in the world. You don't have to create an on-premise data center and implement all everything from hardware to software installations and other things. You have to just simply create an account, implement an instance, create an instance of cloud, and then just upload your data. And you can easily integrate with other applications or profiles using the credentials. So it is easy to manage with a simple UI. Almost not very important programming logic is required. You can go without coding here. It has high availability, durability, fault tolerance as well. It is maintained by IBM and obviously managed by you. It can range with across multiple availability zones. It has API connectivity. You can access with APIs or remote access with HTTP API. So what does it provide? It offers a wide range of services. It has integrated data management, search, and analytical engine designed for web applications. You can implement the search logic. If you want to make a new search engine like Google, Yahoo, Baidu, MSN, you can implement. You can implement the data management, analytics engine. You can implement Google Analytics or other kind of analytics thing if you want. And design with your web application, you can power anything else. You have booked Uber or Ola or Didi and offered a ride. They offer a ride. How they implement their app? They allow you map integration, search, analytics, and wide range of concepts. When you are going to design such an application, you would need a powerful database which has these functionalities, which supports these functionalities. And if it supports natively as Cloud supports, you are in a safe zone. So you can use and leverage the power of Cloud here. It scales databases on CouchDB framework. It provides hosting, administrative tools, analytics, and commercial support for CouchDB and BigCouch. Data is redundantly distributed over multiple machines in form of clusters and other things. So no single node is being oppressed every time. Here are the pricing plans. You can go with a light plan for a simply trial. That is free. You have 1 GB of data storage, up to 20 lookups per second, 10 writes per second, and 5 queries per second. So it is more than enough for a simple beginner. And when you can use this light plan up to 30 days, and you can also get various kinds of coupons out there on the internet using various sites. So you can extend your light plan service usage. Otherwise, you can create a new account, which is obviously legal. Um, and when your requirement exceeds the light plan, you can upgrade to standard or dedicated hardware based on your application usage. So Cloudent is worth giving a hit. You should move with Cloudent. It is very useful. And if you are a developer and really want to build something that is useful to mankind or have a business thing, you can implement with Cloudent. Um, we will be learning more in the next lectures, coming lectures. We will be learning everything from all the concepts, learn the fundamentals about cloud and learn everything about NoSQL database. So if you are a newbie, don't worry, we will be learning everything from scratch. And if you are an intermediate or advanced learner, you could simply watch them because we are running in the fast way. We will not going in depth about basic things. We will just covering. So you could just simply escape or just have a recap all that thing. Um, so this is the end of the first lecture. We will be learning more in the coming videos. Till then, keep learning, keep moving ahead. Welcome back, friend. We are learning IBM Cloud and Database as a Service. And here in this lecture, we are going to learn the difference between SQL, NoSQL, and new SQL databases. So let's start. Let us start with the first database that came into existence in early 1970s, that is SQL or relational databases. As we know, SQL was the primitive database. Actually, SQL is a structured query language. It is a language which is used to query data like reading, writing, and updating information stored in a relational database. It follows the RDBMS concept, Relational Database Management System, where we have data in structured format in forms of table and rows, columns, everything. It uses a single uniform language, data definition language, which is being implemented with SQL. It follows ACID properties, the atomicity, consistency, isolation, and durability principles. Uh, it is difficult to scale and sharding is quite problematic. When we want to implement or and create a backup of our data or strats, it is very difficult because it is not designed for the cluster. It is designed in a centralized environment to work on a single machine. And we could not scale up till after a certain extent, and it could not handle uh, user base as large as Facebook or Google, not even as Airbnb or uh, less very popular sites. Here we have two scenarios. Uh, it is being implemented in forms of table consisting of columns and rows. It is very organized structure. It could consist of information stored in textual format, or you can store images or videos in blob format, binary large object, and other password informations using cryptographic code like SHA algorithm and other things. Now, you could store everything in format of table. The table is stored in a database, and you can create multiple databases. The life cycle is being followed with active, partially committed, committed, and termination. When a database is active, if you want to execute a query, the SQL query, it is partially committed, and after partially commitment, it could go to failover state or committed. If it moves to failed state, the transaction is aborted, or if it is committed, it isn't. We have learned that these properties are being followed in ATM machines or banking transactions, but these days things are getting more complicated, so that these are not as fundamental as back those days. So what are the acid properties? Let us learn about in depth. The first thing in acid property is atomicity. So the data which is being updated using a transaction on a database needs to be atomic or all or nothing. If we want to execute a set of queries or set of things, perform actions, if everything is being committed, only that in that case the transaction is being done. Otherwise, it is not done. Suppose we have a transaction in banking account. We have inserted a debit card in an ATM, and we want to withdraw an amount of $5,000 from the ATM machine from our bank account. If the transaction is completed, That means uh, when amount is deducted from our account, it is provided to our user and everything is as else has been done, then only the transaction is recorded. Otherwise, it is reverted back if anything fails. Then it has a consistency over everything, over records. The data should be valid according to all defined rules. Suppose we have a joint account, joint bank account, and it has issued two credit cards, sorry, two debit cards for both account holders, and both account holders have two debit card, one debit card each, and they enter ATM machines located in different locations and simultaneously withdraw $5,000, and the balance in the bank account is only $6,000 in the earlier case. So the ATM should not allow both users to withdraw $5,000 simultaneously because balance is not enough. So the data should be consistent, and any one of them only is allowed to withdraw the amount. A transaction is isolated. Transaction does not affect other transactions. It means that there could be thousands or even millions of transactions happening each second or each fragment of time, because a bank has numerous customers and they may be doing certain type of transactions each moment of time. They transaction of one person should not affect other person if it is not intended to be affecting. Only the payee or the receiver should be affected. The transaction should be durable. The committed data would not be lost even after the power failure. If the power failure is, suppose in case the ATM machine inverter has gone or power supply has gone, the data should not be failed. It should be recorded in a centralized environment or in non-centralized environment. Then there is a simple graph. There are two graphs which you could understand the difference between NoSQL or traditional RDBMS relational databases. The first graph on the right hand side upper, here it shows the market boom of the new SQL databases or big data. When big data arise back in 2000, at the end of late early 2000, the first decade of 2000s, uh, there we have seen a dramatic increase of the data which is being produced over the internet and such a boom in the big data market. And to accommodate that big data information, either in the formats of Facebook posts, Google search records, and everything else, like YouTube and other data, you have to store that anywhere in a database. So our database has to be changed, and that's why the NoSQL demand has increased. So what is the difference between the database kind of databases is depicted in the lower graph in the left hand side. It shows two curves, one for a relational database, a traditional no traditional SQL databases, and other is a new SQL database curve. When we have little data, the performance is seem to be faster in relational databases, little faster as compared to NoSQL databases. But when the volume of data seems to be increasing, the performance of relational database drastically decreases, and after a certain extent, it won't be working anymore. It has downgraded. It is not functional to handle large amount of request or large amount of data, neither in cluster nor in any other environment. However, the NoSQL databases seem to be intact. Its performance is a constant over different volumes of data, so it is scalable. And when we need scalability or to accommodate markets like big data, we have to go with NoSQL database. So what is a NoSQL database simply? It follows a schema-free and schema-free architecture, and it is built on distributed systems. The data is no more needed to be stored on a single machine or a concise centralized server. It could be distributed over a cluster or over, spread across various regions in the world. It is easy to scale and share. You can scale up anytime you want. You have created an application 1 month ago, and after 6 months, it will see an enormous amount of users uh, after it has been gone viral. And you want to scale up your application, you could certainly do that scale up with NoSQL databases. They follow the principle of eventual consistency, not asset properties, because asset properties are very hard to implement here due to various reasons. They follow eventual consistency, that consistency at a particular instant of time. They follow many type of NoSQL systems. They follow CAP theorem, the consistency, availability, and partition tolerance theorem that we're going to learn in the next slide. The key value, a document-oriented, the graph, column databases are few examples of NoSQL databases we can design. This is a simple difference between NoSQL and not only SQL. Actually, NoSQL does not means they have to oppose everything from the traditional RDBMS. They have different things. We have four types of databases: the key value, column, family, graph, and document oriented. Cloudnet is being a document oriented. Here we have various options available. Like in document oriented, we have CouchDB that is a foundation of Cloudnet. MongoDB, Terrastore, and others. In column-oriented database, we have HBase, the foundation of Hadoop, the Cassandra, which is being used by Facebook, and the graph database, Neo4j, Infinite Graph, Sounds, and so on. The key value database, and like Amazon DynamoDB, that was the first NoSQL database, Redis, Oracle 11g, and so on. Here it is a depiction of the CAP theorem diagram. The CAP theorem consists of availability, consistency, and partition tolerance. It is a theorem which is being implemented for all NoSQL databases. The CAP theorem states that NoSQL database, there is no NoSQL database that could follow all three conditions at the same instant of time, at a moment of time. Only two of them could be fulfilled or satisfied. Uh, we have consistency availability. There are certain databases that follow only consistency availability, but not partition tolerance. There are other databases that follows consistency and partition tolerance, but not availability. So what is the difference between them? Let us understand with an example. Facebook uses the Cassandra database, NoSQL database, where as a Facebook user, write the post and publish it on a file. It is available in the real time to every person, and it is consistent, but it is not consistent at an instant of time, but it is partition tolerant, because at a certain moment of time there could be multiple partitions occurring on the back end of the Facebook data center. So it follows availability and partition tolerance, but not consistency. The number of likes could vary among different users. Similarly, in YouTube page, if you have a YouTube channel and you have uploaded certain videos on YouTube, you might have seen that when after you have uploaded a video on your Creator Studio, it shows you the number of views that are real-time views. But if you check that video from other person's device, there the number of views is less than as shown to you. So that means that data is not consistent, but it is available to every user everywhere in the world, and it is accommodated by partition tolerance. So these are the categories based on what the YouTube and Facebook has implemented their logic. Similarly, we can have consistent and partition tolerance as well. but can avoid availability at the moment. And similarly, the consistency and availability could be followed by avoiding partition tolerance. Here are two kinds of storage that could be followed: the row-based storage, the column-based storage in certain scenarios. Um the column-based storage uh, can be used to scale up in the column direction, the horizontal scaling, and in row-based we have vertical scaling. New SQL database is a new kind of database that tries to combine the acid properties of SQL database or relational database with the scalability and high performance of NoSQL databases. But unfortunately, due to certain reasons, new SQL databases are mostly theoretical, and no proprietary software can apply all these concepts, the acid properties and cap theorem simultaneously, and it limits the spread and adoption of new technology. For this reason, it follows the relational database and uses the SQL query language. Uh, there are different examples of a new SQL database like NewDB, MemSQL, Clusterix, VoltDB, and so on. We have SQL set operations like here, the NoSQL graph operations and NoSQL matrix operations. There are various kind of operations that we could do with new SQL databases. Cloudent is a NoSQL database, obviously, and we have seen the difference between these three kind of databases. We will learning more about Cloudent in the coming videos. Till then, keep learning and keep moving ahead. Friends, we are learning about IBM Cloudent and database as a service, and here we are going to learn about evolution of Cloudent from Apache CouchDB. So let's start. The first thing that comes to your mind is what is CouchDB? Simply put, the CouchDB is also a NoSQL database because Cloudent is also a NoSQL database. It is document oriented. It is being implemented with a concurrency oriented language, Erlang, which is a predecessor of Elixir programming language, which is well known and trending these days. Uses JSON to store data in the document format, JavaScript as a query language, supporting MapReduce, and HTTP for an API. If you want to insert any record on this CouchDB or retrieve any data, you can pass that statement via an API over the HTTP. And you can use JavaScript, which could be easily implemented in web and mobile applications. CouchDB implements a form of multi-version concurrency control, MVCC in short, so it does not lock the database files during writes. In traditional databases like RDBMS and other kinds of databases, uh, multiple write operations are not supported. Only a single user or person is allowed to perform a write operation. In case multiple writes could occur, they uses a lock kind of locks to conceal a certain section of codes. So multiple writes are not supported there. But here it supports a multi-version concurrency control or multiple writes, and it does not uses the lock. The conflicts, if occurs, are left to the application to resolve. The resolving a conflict takes first merging of the data into one document and then deleting the stale one or the contradictory one. The other features include document level ACID semantics. The ACID properties are followed on the document level. A certain document, if a particular document has to follow this ACID properties, when multiple documents are considered simultaneously, the ACID properties are not followed. With eventual consistency. Eventual consistency means that availability and partition tolerance of cap theorem. One of the CouchDB's distinguishing feature is that multi-master replication is supported. In other similar kind of databases like in NoSQL databases like MongoDB, Cassandra, others, there are no multi-master replication. Only a single master is there for replication and other purposes. The multi-master replication allows CouchDB to scale across machines to build high-performance systems. Here it is a dashboard of CouchDB. Here we have various options, databases, active tasks, configuration, log, start replication, and other options as well. We can create new databases, set permissions, migration, and other things. The Cloudent dashboard seems similar to this, but the difference is that the Cloudent runs on the cloud, and the CouchDB is meant for a device or system. You could install CouchDB on your PC or your server environment, and you can always migrate from data from CouchDB to CloudEnt and vice versa. Here it is a CouchDB ecosystem. Um, the cloud provides the infrastructure tools and services not specific to CouchDB because Couch does not actually being implemented on the cloud. It has backend services, the backend service owners, integration consultants, hosting owners, the component store, the app store, the content owners, the front end services like B2B or business to business, business to consumer, and other and user services, and different options. It is implemented in various scenarios. So there are some features that makes CouchDB, Apache CouchDB distinguish or ahead of other databases. It is built for offline. So if you have an Android application or other kind of mobile application and you turn off your internet over a time, turn on or off, when your application internet connection is off in your mobile phone, the data could not be um, synchronized over the storages, but CouchDB can replicate devices data that can go offline and handle data synchronization for you when the devices is back online. So you don't need to worry about synchronization of data. It could be automatically done by CouchDB. It follows eventual consistency. It is being implemented with a distributed architecture and replication in mind. So multiple replicas can have their own copies of the same data, modify it, and then synchronize those changes at a later time. It follows ACID semantics in a multi-version concurrency control and can handle high volumes of concurrent or simultaneous readers and writers without conflict. It supports HTTP API. All items have a unique URI, uniform resource identifier that gets exposed via HTTP. It uses HTTP methods like get, put, post, delete, and other as for basic CRUD, create, read, update, and delete operations for all resources. You can leverage HTTP method and it could be implemented in a scenario like if you have a website and you can write JavaScript code on the back end or the front end which implements the HTTP calls using these methods on the database. The CouchDB also offers a built-in administration interface accessible via web, which is called as Futon. Here is a brief difference between CouchDB and MongoDB for let you distinguish between other NoSQL databases and CouchDB. So the data model of CouchDB is implemented with JSON, whereas in MongoDB it is being implemented with a binary JSON or BSON for short. It has an interface called HTTP and REST. It follows HTTP API over REST. And similarly, the MongoDB has a custom protocol over TCP/IP. The object storage is based on database which contains documents. And in MongoDB, the database contains collections, collections contains documents, and so on. The query is being implemented with a MapReduce, JavaScript plus others. And here in MongoDB, we have again JavaScript for collection, object-based query languages. We have replicas, the master and custom conflict resolution functions in CouchDB. And in MongoDB, we have master slave implementation. The concurrency in CouchDB is MVCC, multi-version concurrency control. And in MongoDB, we have update in place. And there is no MVCC. The CouchDB is implemented with a concurrency controllable language, that is Erlang, while MongoDB is designed with C++, that is object-oriented and procedural as well. The IBM Cloud End, what is the difference between CouchDB and IBM Cloud End? Uh, First thing is that IBM Cloud End is an advanced form of CouchDB. It is a cloud implementation. The cloud version uh, kept scalability in mind, and it has various modifications because it was designed for a large hadron collider project. So it has horizontal scalability with respect to data size. We could scale up data horizontally. The Cloudent offers full text search, whereas CouchDB doesn't offer full text search. We can search full text, full file, complete file, whereas CouchDB searches based on keywords. It breaks down the text into keywords, and based on that, it uses the search algorithms. Cloudent has a different authentication system. Cloudent has a Cloudent query, which allows you to declaratively set indices and query the database. Whereas in CouchDB, there is nothing like a declarative query with Cloudent query or similar thing, where you could not set actually indices or query on the database. You have to use views in case of CouchDB. So this was a brief introduction about CouchDB and how Cloudent has evolved from the CouchDB. The difference between those and what makes it CouchDB or Cloudent different from other NoSQL databases. So we will be learning more about Cloudent in the next videos. Till then, keep learning and keep moving ahead. We are learning about IBM Cloud and Database as a Service. And here in this lecture, we are going to learn more about Cloud and getting in-depth view of Cloud. What are the capabilities of Cloud, what are unique features to Cloud, and how we can implement those in our current scenarios. The Cloud has different advantages. It has full text search. You can search complete text along with searching of the keywords separately. You have advanced geospatial capabilities. You can leverage the functionalities of a map, the world map, an aerial map, anything like that. It supports native mobile software libraries uh, for Android, iOS, BlackBerry, and others. It supports private, public, and hybrid cloud. It could be implemented on all three scenarios with a combination of other services with integration of those. We can store our location-based data in a popular GeoJSON format for the geographical information systems or GIS in short. These days, cities are getting smarter, and with getting more smarter, we have to build 3D maps or 2D maps of each city, every lane, every drainage system, and everything else. For that reason, we need GIS, and GIS is put together with a GeoJSON format. We can store all the data related to map in our cloud and database. We can ensure the integrity of offline data access using synchronization of the cloud when internet connection is available or not. We can do more ad hoc queries over our net data. It includes pre-built connectors to popular analytics tools like Apache Spark, IBM-DB, enabling you to explore your application's JSON data and uncover business insights with ease. Analytics and data warehousing for JSON is also an advantage of this. We have JSON warehousing facility for geospatial types and other types, uh, bringing it into a Spark cluster with SQL warehouse where it could be explored, analyzed, and visualized. We have various options with Cloud End. We can do more like data layer. We have CouchDB. We can change transfer our data from Cloud End cloud to CouchDB on offline mode in a system-oriented design. Uh, we have Dynamo to be included for clustering and scaling. We have Lucene for querying and text search. We have GeoJSON option available to us for geospatial indexing and query. We have Jenkins for continuous integration, the DevOps tool manager. We have Connectivity for metrics collection, RSyslog for federated logging using uh, Facebook, Google, and other things, similar to Amazon Cognito. We have Graphite and Rayman monitoring. We have Chef, the configuration management tool. We have HA proxy for DNS geoload balancing. Here are the primary usage of Cloudin. We can build the document lookup, direct basic CRUD operations, create, read, update, delete operations directly. We can build primary indexes, we can build secondary indexes, we can build search indexes, we can use cloud and query, and more. We will be learning each of them separately in separate lectures, and we will be going to perform practical operations, each on document lookup, primary index, secondary index, search index, and cloud and query. So this is a simple scenario where we have geospatial map where we can place anything like that. Suppose we have to design a system for a metropolitan city of New York City. We have a 3D map or 2D map of a city where we have data about the crime rates in scenarios. We have a particular location, the incident of crimes like pickpocketing, chain snatching, and such things, and we have our data over there, and we have to ensure in which locality the density of crimes such that number of policemen are allotted based on occurrence or possibility of crime. Suppose in lower Manhattan, if say there are more crimes as compared to Brooklyn, so we need more policemen in lower Manhattan as compared to Brooklyn. Similarly, we can perform a huge range of tasks more complicated than this by using this GeoJSON or map cases. We will trying to build that thing in our case. So this is end of this lecture. We will be learning more functionalities by experimenting and building things in the coming lectures. Till then, keep learning and keep moving ahead. Friends, we are learning IBM Cloud End, and with Cloud End, we need to learn based different concepts like JavaScript, JSON, CURL, and other things. So in this lecture, we are going to learn about the JSON, the JavaScript object notation, and CURL, the tools that are widely used with Cloud End. So first, let us start with JSON. JSON is a language-independent data format. It is used to store data in forms of documents where we have key value pairs or attribute value pairs in format of text to transmit data objects and array types and other things. We can store data specifically with encrypted or unencrypted in plain text in human readable form that can be used to as a database. The documents serve as a table as compared to relational databases. In relational databases, we have table, and in with no SQL database, we have a document stored in JSON. Where in the tables we have rows and columns, and here we have key and values. It is used with NoSQL databases as a collection of JSON documents. It is a simple JSON script. It is a document written with JSON. Here we have parameters or things in plain text. The things that are written within quotes, double quotes, like underscore ID, department, name, title, address, these are called as key. On the left hand side with white color, and the other things that are also written in quotes followed by colon, they are values. The values are written with a blue green color, and they have to be separated. Each key value pair has to be separated by a column, which is a delimiter. And as other programming languages, we have numbers, string, nested objects, array, boolean, and other data types. If you want to declare a number, suppose we have a department and the value for department you want to assign is 23. So you can do so by creating a key called department and assign the value 23 to that department. Similarly, if you want to initialize a string, you can do so by writing the name, suppose the key and the value within quotes. The string consists of characters and the number consists of numeric values. Similarly, we can have nested objects where a key consists of multiple key value pairs. Suppose there is address. In address, we have street address, city, state, everything. We have to place them in a parenthesis. Similarly, we can have array where multiple values could be assigned to a single key. Suppose we have skills like Cloud and NoSQL JSON, which could be written within square brackets separated by comma value. And at last, we have Boolean value, which may take values like true and false, yes or no. Yes or true is written with true, and false or negation is written with false. It is not written within the quotes, double quotes, and if it is a last line, anything, number, string, nested object, array, boolean, they can be jumbled. It doesn't mean that we need to write number at the first and string at the second. Anything could be at any place as per your requirement. And when you are declaring last line of your JSON file document, you don't need to place a sem comma, and all values have to be everything, each text, each line has to be placed within a parenthesis in the document format. With Cloudent, we need to provide ID, which is the default parameter. The first parameter that is to be provided is underscore ID, which serves as the primary key for this document to identify it separately or uniquely. So this is the way how we write, how we will be going to write each the documents and everything, every data that we're going to store with our database in the cloud. And this is the format of writing that thing. Then there comes a very useful utility called as curl or curl, which is a command line tool for getting or sending files using URL syntax. You could make request, perform port, post, get, delete, and other operations, HTTP operations, via command line mode. It supports a range of common internet protocols like HTTP, HTTPS, FTP, etc. It performs SSL certificate, Secure Socket Layer certificate verification by default. There are a huge range of commands with curl. You could learn from them online. You could find those commands or install the curl on your system. It is an alternate method. You could directly perform by the website using the JavaScript, or you could go to Cloud and dashboard and perform operation directly from there. Uh, this is the below line, last line is a simple example of a curl syntax. Here we have to write command curl, provide an argument. Suppose here we have a -o argument and provide the URL and a file. We have file or web file example.html. We want to upload that file to here, and we could perform multiple operations with curl. These commands are to be executed on the command line interface like a Windows command prompt or Linux shell, and we have to install the curl utility first before running these commands. Uh, with curl, we don't need to re-authenticate our access. With a pre-authenticated version on CLI, we do not need to provide username and password each time for running each command. Otherwise, we need to have uh, to provide password or username each time. We could perform those operations without using curl, but we need to provide the credentials. We can also create aliases for different options and commands that allows us to write those commands in shorthand. We can create an alias in Linux by writing using the command alias by shortening the long syntax. So this was a brief introduction about the JSON and curl that we are going to use in our application with Cloudend. If you want to learn more, you could explore or you could practice yourself. These are not very tough things, they're very simple, but they are fundamental things. That's why we have covered. We will be learning more content on Cloudend and begin with primary index, search index, and other things in the coming lectures. Till then, keep learning and keep moving ahead. Friends, here in this video, we are going to create an instance of Cloudend, which could be created by logging into your IBM Cloud account. You have to log in with your IBM Cloud, move to Catalog, and scroll down a little bit to find this service called IBM Cloudend. Uh, Let us search this. There are a huge range of services on IBM Cloud, the bluemix. Here it is, the Cloudend under the databases category, which is available as a light version offered by IBM as a company. And we already know what is Cloudend, so no need to introduce the Cloudend to you. You have to create a service of Cloudend uh, by providing a service name, choose from region or from resources and other options. We have to provide a name, choose a region, but we are choosing a US default because various options are available in this region are supported in Germany and US South. Some features are not supported elsewhere else. You can choose the authentication method, either both legacy credentials or IAM, similar to AWS. You can set the pricing options. We are using the light, currently the free pricing tier. If your data exceeds this free tier, you could choose from a standard or other options, and you will be paid a charge only for what you use. Hit the create button when you are ready to create the cloud and database. Create an instance for this thing, and you can do this for absolutely no charge. So here it is. It is created under the data and analysis category. You can manage these services, set credentials, have a choose from plan. Here you get a support if you want to raise a query, or you could raise a ticket as well. Here you have to create a credentials first, uh, provide a name for the credentials, select ID, or if you want to provide any additional configuration parameters, you could do so. Otherwise, keep it blank, simple as possible, and hit the credential create button. The credentials will be created. We are going to use these credentials, the API key, the host, IAM API description, and other things uh, for future references. We have to use the password and the username, the ARN, and everything is useful. Uh, Here, this is the CRN, the IAM service, the password field, a username and password is a most important thing that you are going to use. So keep it separate. Uh, you have to use and verify in cases when you are creating a migration, sorry, replication and other things, or you could choose from elsewhere else. You can set up connections with other tools, other services, or move to dashboard. You can create connection with other Cloud Foundry applications. Currently, we have not connected to anything else. Then you can launch Cloud and Dashboard. It will redirect you to the Cloud and Dashboard. It will take some time, so allow it. We are going to learn about the dashboard in the next video. Welcome to Cloud and Dashboard. We have created an instance of Cloudent and where we have multiple options like monitoring. We have current operations, the storage, the geospatial index, search index, views and databases, everything which is being displayed here. We currently have nothing created yet. We have databases. Currently, we don't have a database created yet. We could find replication, active task, other things as well. We can create database from top right side. Here we have an option to create a database. You have to provide a name for your database and hit the create button, uh, which will create a database. We have created a database, and here we can create the document for this. We can create multiple documents as well. We can perform queries, set permissions, and various things. We have animals Africa as a database. Here it has automatically generated an ID or primary key for our document. We could revert it back. We have a query option where we can run the cloud and queries using selector fields and sort options in MapReduce manner. Here we have permissions we can change. We can access design documents. We have various options like query options, the keys, and other things. We have a replication option where we can create a replication of an existing database either on our instance or from other locations. We can create a replication by defining a source location, the source type, the authentication. Using the authentication, if we have permission, we could not create a replication unless we have a permission. We have to create a target database, provide a URL, and everything else. We are going to learn these things by implementing. We have active tasks. Currently, we don't have any active tasks. We can set replications, indexers that is running in the background. Similarly, we have account where we can check back our account lookups, everything, whether we are running in a free tier, and we can set our plan calculator, the charge, the amount, and everything else. We could find these things specifically for Cloudent. Otherwise, you could go with a billing section on Cloudent. Sorry, on bluemix. We have support and documentation with Cloudent. We're going to learn everything by performing practical, the application, the database creation, everything from query and everything else. So no need to worry. You can set your standard plan calculator from minimum to maximum and everything. Um, Similarly, the account it runs by various announcements. We have announcements. Suppose there is an updation to the cloud end, you would be finding it in the announcement sections here. Similarly, you can enable the cross origin resource sharing or CORS, which lets you connect remote servers directly from the browser. You could enable or disable CORS. Currently, it is enabled by default. You could disable CORS anytime you want. You can create a case or tickets which could be answered. You can raise a problem or question, and IBM staff will reply to your question. You have a documentation support for the complete API and everything related to cloud, and that is being supported by official IBM. So there is a support and everything in case you get into a trouble. We have notification section where you could find notifications as well. We just find the current database created successfully, the alarm, and every informative notification and all notification in the bell icon on the top right corner. Welcome back. Here in this video, we are going to delete a database that we have created earlier, the Animal Africa, and we will be going to create a new database from the beginning. create all the doc files, and provide the entry in the format of JSON. So let's start. To delete a database, you have to provide the database name again by typing it for confirmation. This is also common in AWS and other environments. And here you have to provide a username and password for this profile. This is not the username or password that you have created during sign up on the bluemix account, but the cloud instance. From the credentials, you could find that username and password, and it is being deleted. You could do that thing. And now we are going to create a new database. By top right corner, here you have a create database option. Just provide a name for our database like Asian countries. We have this thing, and we have created a database of Asian countries. Here we will create separate documents for different countries. So after creating a new document, here this is the default thing. You can change the ID value anytime you want, but it must be unique throughout a single database. So suppose let us define a country for Japan and provide the data for Japan. We have key value pairs here. We are assigning Tokyo as a capital for Japan. We have to place both key and values in double quotes, the capital and Tokyo as well. The common because both the variables are string type. In the earlier lecture, we have learned about the JSON, what are the different data types supported in JSON, and we are going to implement such types here with a demonstration application. So we have provided the capital Tokyo. Then we could provide a Human Development Index (HDI), let us say 0.903. It is a numeric value. It is a number, so don't need to write any codes. And we can write major companies or corporate sector operating in that country. Uh, um, Provide a colon. We have to separate each key value pair uh, from a comma delimiter. And here in major companies, we are creating a key value pair, the nested objects, which are implemented within the quotes, curly brackets. We have two companies, Sony and Hyundai here, both dealing in different categories. Sony is in the under category electronics, and the Hyundai is in automobile. Similarly, we can write more data, and we can always choose to update our database anytime we want. You could update your database by remotely using curl or HTTP API or directly from this dashboard as we are creating now. And we are providing a Boolean value as a developed. It is a developed country. Japan is a developed country, so I'm providing it true. The value is true. Then we have major cities in Japan. The major cities we want to provide it in array. We have Osaka. We are providing this data type as we don't have key value pair. We have only values. So Osaka, Kyoto, Hiroshima would be the cities, the major cities in Japan other than Tokyo. So this is we are creating a table as compared to relational database, you must say. Here we have different values, the entry, and supporting different data types as well. Similarly, we could create more content, and we have this file created with ID, key, and values. Um, Here we can change of the permissions, view the table. The table is showing in the column or row format. Here we have single entry. Similarly, we can add more entries or more document in the ID, HDI, capital, development index. major company, we have various categories that we have created, the key value pairs. The key is showing on the top, the value is showing in the bottom. Similarly, we could create more documents or more tables or more records for the same thing. Suppose I want to create another country for, say, uh, Bangkok is the capital of Thailand. We want to create a country for Thailand. Add some detail. You don't need to provide every entry for each data, each table. Suppose we have uh, uh, hundreds of Asian countries, and all countries don't have developed cities or major cities, only one single city. For Singapore, for example, so we could skip other entries. Suppose we have not declared SDI or major company in Thailand example, so it is well supported. We don't need to provide all the values. We can choose to set permissions from the permission tab. We could set admin, reader, writer, replicator permission. We have to generate API key if you want to access the cloud and database uh, through HTTP API. You have to provide that access for authenticated or unauthenticated access. Uh, Notification will be shown on the top as a message when database permission or anything you modify. Here we have a key and password for our API keys. We can use it for remote authentication. It is valid only for our current database that we are working on, Asian countries here. So it will be available for this thing. It will show the number of documents, the overall size, and here it is. We have this account. We could run query, change, perform changes. We can see what changes are being done, reflected back in new documents or the earlier ones. You can grant a database permission to any user. Just provide a name, anything, and hit the grant access, grant permission, and check all the options that you feel like. We can move to sequences, and we can here easily find what are the changes that are being performed in our database. You could see metadata. Here we have revision information, the revision REV, the revision history, the ID, which is primary key. Revision history always get implemented when we update our database or table entry. It is automatically generated. We don't need to provide it. Similarly, we could execute a query. We could run queries based on MapReduce, the environment here. We could create a JSON format table. And so this was how we could create a database, a document, and entries and set permissions. Um, and next, we will be learning about replications and more. Welcome back, friends. Here in this lecture, we are going to learn about HTTP API and how we can leverage it for performing various operations on our cloud and database and all the database data. So let's start. So first of all, let us learn about what is an HTTP API actually. So HTTP is a hypertext transfer protocol, which is a network protocol acting whenever you connect to internet or perform various operations over a network of computers. So it is a protocol to exchange or transfer hypertext. And what is hypertext? Hypertext is a structured text that uses logical links or hyperlinks between nodes containing text. The text include different kind of data set like a cookie, the status codes, the web pages, and other things. So it is a protocol to exchange everything. Whenever you try to open a website or create a connection between two sites or two computers, you use HTTP in one or other way. With CloudEnd, we have a proper format where we can use this HTTP protocol to uh, transfer data or share data or allow remote access. So the API for HTTP would be different sets of commands or the format that we could use. So let us learn more about this thing. So what is an HTTP and how it works? There are four basic options that we could perform on a database. We have create, read, update, and delete options, the CRUD. And if you want to create a database, you have to write a HTTP put or perform the put method. These are the methods. The put method is used to create an entry in a database, in a document. If you want to fetch certain records from a database, you could use the get method, which is used either in query string or other formats. Then, if you want to update a database or provide information, insert or update, you could use the post method. And finally, if you want to delete any entry, you could use the delete method of HTTP. When a computer started connected to another computer or server, it sends a GET request, and the response code is being heard by the uh, requester. So when it founds a request status code like 302, it says that all is working fine. We can get 200 or 200 for OK or 404 for not found. We could execute uh, in a web URL. So HTTP API design consists of two kinds of things, the HTTP request and HTTP response. A request is made from a system that is requesting certain information from another system. Let us say we have a desktop in our scenario and we want to fetch information from our cloud and database, which is stored in any region of IBM cloud. And the region, the system, the server where our data is residing is the replying the host of the application. We want to send request to that server, and the server will provide us a response. So we will sending an HTTP request in format of headers, method, URL, and body, where headers consist of cookies, the user agents, language preferences. The method consists of get, post, put, or delete, or other method, whatever we are using. And then we are providing the URL to particularly access that particular database or a location of file. Then we have the JSON file or any other kind of file that we could attach in our body. When it is sent and the request is fetched or accepted by the server, it will send us the response after searching the file whether it exists or not, or whether it is able to perform that operations based on certain authentication and other parameters. We have headers. It will return you the headers and the cookie cache control for catching up whether you are the same user to generate a session. Then it will send you the status code, the 200, 302, 404, and other status codes. Then provide you the data in format of HTML, JSON, or binary data, or any other format. Suppose if you are requesting any entry, suppose you want to view all the entries currently available in your database table, and it will respond to you via web page. So it will appear on your screen. The cloud end follows an hierarchy where we have an account on the top level. The account is your IBM bluemix account or the cloud end instance, which may have different databases that you could create from the cloud end directory. And we can have multiple documents in each database where document acts as a table entry, and it would contain a key value pair designed in a JSON document format, and the document could consist of multiple attachments like image, videos, and other informations as well. So this is the hierarchy that Cloudend follows. And from now onwards, if you are using the database document and attachment word, don't worry and remember this hierarchy. An account can contain of multiple databases, multiple data, each database consists of multiple documents. A single document can consist of multiple attachments. So this is a way how we can make an HTTP request by executing the HTTP API. We have to write the HTTPS or HTTP and provide the account name. Here our account name is addblanks.cloudend.com. So this is the account name for the IBM bluemix or other thing. Here we have a data. We have to provide a database name separated by a slash. Now, after we have provided our database name, then we have to define the endpoints that we are going to manipulate. Here we are going to manipulate the all docs document, and where include documents is equals to true, we want to display that document. Similarly, we could execute any of the methods get, put, post, delete, and copy, uh, where the following format: the HTTP verb, header, data, and account, anything else. And we could perform this HTTP request not just directly from the browser by tapping in the URL panel. We could also perform this from the command line using the curl utility. We have to provide this. We have to first install the curl in our system, and so that we could execute this thing. And we are going to run the curl from the command line after we have authenticated using the same username and password that we have seen in the credential section of your Cloudent instance. When you create a Cloudent account, you have to create a credential, and there onwards you have the username and password that you have to provide. After you have provided that thing, you could perform HTTP request using the curl command and write the syntax as here in the last line. The curl -x is an argument, that is verb. We have get, which is an header, or you have can provide more arguments. Then you can provide data and the location of the document. Here we have the addblanks.cloudend.com account and all DBS is the databases we want to fetch. So this was a brief introduction about the HTTP API and how we can leverage it in a Cloudend scenario. We are going to learn more about other things in the Cloudend. So till then, keep learning and keep moving ahead. We will be learning more in the coming videos. Welcome back, friends. Here in this lecture, we are going to learn about replication and how you can perform replication on Cloudend and what are the various kinds of replication that could be performed among different databases. So let's start. Replication is a thing which synchronizes the state of two databases so that their content are identical. It is actually a synchronization among two or more databases, basically two in one step. And if you want to synchronize three or more databases, you have to repeat into different steps. Suppose we have a certain set of information in our database one and other set of information in another database, and we want so a case when all the content of both the databases are same. The thing that are missing in one, the first database have to be copied from the second database, and the thing that are missing in second database has to be copied from the first database uh, until their contents are identical or similar to each other. Here we have different three kinds of replication, the, and we will learning about them. Uh, so the first thing is the continuous replication, the first type. Here we have different clusters, the cluster A, cluster B. We want to replicate both in the both direction. Here nothing is source and nothing is destination, or both are source and both are destination. If we are saying with respect to the first cluster, the cluster A, uh, if we want to we have to push the data that is missing in cluster B, and we have to pull data from B that are missing in A, our current cluster or database. Similarly, we could perform this thing in cluster B also, and until both are in synchronization. But continuous replication can result in a large number of internal calls. It is a disadvantage and it might affect cost. So the continuous replication is disabled by default on Cloudend, but in other databases you could find it being enabled. You could always choose to enable among the continuous replication and other options as well. So let us understand about the next thing, the singular replication. Here we have only one source and one target. Suppose we have a cluster A or database A, which have extra amount of data, and we want to fetch that data from cluster A to cluster B, or copy that data into the B until both are in sync. We have to make a push request from cluster A to cluster B. Cluster A is a source and cluster B is target. Then there is a filtered replication where we want to fetch information, but based on certain criteria. Suppose we want to, if we want to copy text from A, where text could be an essay or anything else, and we can define the essay must have a foo statement or anything. The essay must be addressed to Andrew or anything like that. We could perform various kind of filter based on the programmatic access, which is implemented in JavaScript, or we can also perform sorting a filter function in design document as well, which is written in JSON format. All the replication on Cloudend follows the append only storage model, uh, where a data is always added, which is being missing. It won't delete any data from your existing database or cluster. If for any reason there is a network problem or node fail, there is no corruption of data due to this append only storage model. When you start the database again up, the replication will pick up where left off. So if internet connectivity was lowest or due to power failure or anything, the database will start up again, not beginning from the first thing. It will pick up from where it was left. Suppose you have 40% replication already done, and due to certain reason your system crashes, and whenever you power back again or connect to the internet and the replication starts, it will start from 40%. It won't start from 0% again. It uses checkpoints to keep track where left off. The checkpoints are stored on both the clusters, the source and the target, and only change data is replicated. If the data is common, it is not being copied. It saves a lot of bandwidth or internet speed. So this was a brief introduction or a theoretical implementation about replication, the types of replication, and how we can perform replication. We are going to perform replication in the practical video coming next to this. So you keep watching that video and try to implement the same thing uh, by your own account. You should have a bluemix account till now, either the free tier or the paid version. You should create the cloud and database, watching the video and try to implement everything what you're learning, either in the theoretical sections or practical sections. If you have any doubt, you could ask me anytime. So we are going to keep learning and keep moving ahead. We are going to learn more in the coming videos. In this video, we are going to create a practical replication demonstration. We will create a replication of a database from a source target to target. Here we have a source database. You have to provide with a replication section. You have to provide a remote database. We are replicating a remote database. You could also replicate a local database that you have created on your instance on Cloud. And we can also replicate a remote database that is a database of other user with a provided URL. If he or she, the database admin of that remote database have allowed it for unauthenticated user. You could directly access, and otherwise you need authentication. Here we have to define a target, the database that we are creating. We have to provide name of this new database, and we have to provide authentication, the same username and password from the credentials that we have created, and we can create a replication document out there for and provide a name for that thing. And here we are doing a one-time replication uh, from the remote database. We can provide the cloud and API key with the same username and password from the credentials. We need to copy the username and password from here. So simply password would also work out. Then hit the start replication option. We have to provide the username as well. This is not the username. Same from the credential. This is on authentication to verify whether we are the owner of this thing or not. So this is the application. It is being created. It is showing the source location, the target, the URL of those things, those database, the start time and type of replication, one time continuous or filter replication. The state is currently running, so it is creating a replication. And after it has been created, we could access our values. It has these are the value of this newly created or replicated animal DB database. We have the JSON data format, everything arranged here. We have ID, artwork, the badger, and everything. We have replicated that database successfully. We can perform any kind of operation here. The original database that is kept remotely is being intact, and all changes we make apply to this database that we have replicated. The entries are same. We can modify it, set permissions, and everything else. You could perform query, various operations, uh, and access this thing from database. It is also being displayed in the database. A replicator name has been created with a database, and animal DB database is created here. It is showing the number of documents and more. Now we are going to check status of our application job. We could do so by moving to replication section or with the database section. And here we have created various databases which are being displayed in the database section. In the replication section, we have the replication history. We have three options in the action category. We have settings. We could edit replication document and delete replication document. In the replication document, these are the required fields, the ID and the revision. The ID is the primary key, the revision is the revision history. Then there comes the user account permissions for the user. Then there is source and target information. And here the information along with the statistics of replication job. We could check all these values and we can edit it anytime we want. Uh, we can check status that our application has been successfully completed or not, and we can reflect back. It could be reflected back to all the documents. Friends, we are learning Cloud End, and here in this lecture we are going to learn about certain use cases of Cloud End database. So let's start. The replication use cases involve various kind of services or scenarios where we can perform replication to or from various kinds of cases. The cases include the CouchDB. We could replicate from CouchDB to CouchDB or other cases. We can perform replication on Cloud End Database as a Service or Cloud End on the cloud, IBM bluemix. Then we can create application for cloud and local or private cloud uh, in private data centers. Then we can perform replication across mobile devices using cloud and sync. Then we can replicate with PouchDB and TouchDB. So let us learn about each one by one. These model for geographically dispersed clusters to set up a very resilient, highly available disaster recovery capable mega structure is to be done. The cloud end replication is compatible with any database with CouchDB supported style replications, and which could be used in hybrid cloud scenarios. Here we have a public cloud and a private cloud. The public cloud is also called as a cloud and database as a service over the cloud, and the private cloud could be termed as a local data center. And we could create replication to or from public and private clouds. Then the second use case is we can replicate our database developed using CouchDB on a personal computer in offline mode. We can create replication of that database in CouchDB on a PC to the cloud and database service over bluemix. Then we can create a replication for mobile clients via Cloud and Sync or through a web browser using PouchDB. A common development software development cycle activities to perform a singular replication of production database to a development environment for building a quality testing, a QA testing. We can use the replication in this scenario as well. We can also use a replication for data backup in case our data is very crucial and we don't want to lose it anyway. And we want to create backup in either local or in other cases on over the cloud as well in form of other database in other location. We could create two kinds of backups, the hot backup and the cold backup. The hot backup is called continuous replication that we have learned earlier. In this, we have to create a replication of our database continuously over time when a new data is being added to the archive section in the backup center or in the currently used database over the cloud end. Then there is an option for cold backup that we usually make over time, change of versions as well, and it could be done periodically over an instance of time, over weeks, month, or annual year period. So this was a brief introduction about various use cases of clouding. You could develop your own application or build your database scenario and create a replication as per your usage. We will be learning more in the coming videos. Till then, keep learning and keep moving ahead. We are learning replication on clouding, and we want to replicate a database either from remote location or from remote user or from the same user from one database to another database. Uh, we need permissions to set up on the target and source databases to be installed at first hand before performing any replication job. We're going to learn the same thing in this lecture. So let's start. To replicate the database between accounts or between a source or the same account, the cloudent requires that account holders have the correct permission for both source and target databases. For the source database, we need to have a reader and replicator permission to be set up. The reader permission allows a replicator to read our data, and a replicator permission allows him to replicate the database. But don't check the global replicator permission uh, for anyone to allow that thing. Then for the target database, we need to set minimally reader and writer permission. The writer permission would allow him to write his own database. To share the design documents, we should have admin permission as well as set up with reader and writer permissions. But don't check any options with the admin permissions because you don't want to share the admin privileges, just the design document. Replica role allows a replicator to write checkpoints but not to have world writable permissions on the database. Use a replicator and role along with a reader mode if you want to provide credentials to another party to replicate a database without giving world writable permission. So this was about various kinds of permissions that we need to set up with the source or target databases, target in minimal configuration, or to share the design document, or to write checkpoints, or to share the credentials. Uh, we could implement these permissions by going to the Cloud Enter dashboard, and where we can set up permissions for each and every databases. Not all databases need to be set up the same permissions, and you can always choose to change your permission for each database anytime you want. And you can create roles for different users as well, and you can separate the global permission from any certain user's permission. You can always grant and revoke the permission because you are the key holder. Once a database has been replicated, you don't have control over the remote target database. Only you have the source database. So try to provide permissions carefully. We will be learning more in the coming videos. Till then, keep learning and keep moving ahead. Friends, we have now a little grip over IBM Cloud and Database as a Service. After learning about a few things like replication and other things, here we are going to learn about crucial things that are unique to CloudEnd, or if not unique, they are first to be implemented with CloudEnd, and which makes CloudEnd really stand out in the NoSQL database scenario. So let's start. Here we are going to learn about indexes and queries. Indexes are built for different reasons. Suppose the first case where we have created a database which consists of documents, and documents consist of data, the key value pairs and everything in JSON format. So after we have created a data, we are interested in performing certain types of operations that could be classified as CRUD, the create, read, update, and delete operations. We want to create more data. We want to read that data. We want to update our data. We want to delete certain data. So how we can do it? If our data is not very complicated, a database is not very complicated, we can perform direct document lookups which can perform basic CRUD operations on documents by directly referencing documents using document ID, the underscore ID key that we have defined in every document that is automatically generated, and we can change the value to get a document by its ID. But we have to build indexes for additionally say primary index. Additionally, the cloud end creates primary index for every database out of the box and stores in a B-tree data structure. The cloud end automatically creates a primary key, primary index, and you don't need to create it actually, which is stored as B-tree, and cloud end uses document ID as the primary key, similar to perform CRUD operations to get list of documents by their IDs. Then we have view. If you have been using database earlier, the relational databases, you might have gone through a thing that is called view. You have to create a view for certain reasons, which is called as a temporary table, or to perform various kinds of mathematical operations like average or other operations. Similarly, we have secondary index for the reason if you have a query involving more than lookups by the primary key, you don't just need a primary key for fetching certain information. You will need to build an index. The secondary indexes are built to wear up the map reduce paradigm. We want to query in a MongoDB fashion, and we have to build a map reduce paradigm after we have a huge range of data. We have to perform MapReduce operations on them for analytics such as count, sum, average, and such operations. Then we have a search index that is unique to Cloudend. which are built using the Lucene search for ad hoc queries or temporary queries on one or more fields. Searches involve large blocks of text or queries that require additional Lucene syntax like wildcards, fuzzy sets, and phase sets. We are going to learn about them in the coming videos. Then we have to build a geospatial search, geospatial index. If we have to work upon map, suppose you want to build an application like Uber, Ola, or car application where you need to query about the different locations. You have to fetch information about the locations kept in the cloud in DB or other scenarios. You need to build geospatial index in that case, which is stored in the most efficient way to allow for four-dimensional query for advanced geospatial query beyond the bounding box or 4D. You can perform multi-dimensional query far more than four-dimensional. The three-dimensional could be length, breadth, height. The four-dimension could be the quality or additional data, whatever you want to add. But there is a condition for reading documents from cloud and database. If we want to have a higher performance, we should prefer primary index over secondary index and the cloud and search. Or if we want flexibility, more flexibility to our developer or user, we could go with cloud and search, then prefer secondary index and then primary index. We have to balance between flexibility and performance to bring out a better result. Then we have a cloud and query that is similar to SQL in relational databases, where we can perform queries directly over the database, going through the bluemix console and a cloud instance. You can use a MongoDB style or Mongo style querying and provide you with a declarative way to define and query indexes on your database. If you prefer Mongo style querying for searching and multiple logical operator, we have to use the same syntax as we are using with MongoDB. Uh, we will get examples of that. Then we have design documents. It is a new concept here. These are the special documents in the database whose ID are the design underscore design, name of the design document. You can define the name of the document, design document, and edit it as per your usage. A database may contain one design document with several views and search indexes, or you can have an individual design document for each index that you create. For secondary index, search index, a geospatial index, which are defined in design documents in the database, contains the index functions written in JavaScript. So this was about a certain concepts that we are going to implement on CloudEnd, and these are the functionalities that makes CloudEnd very special. You can perform all kinds of operations, the CRUD operations and basic operations, similar way as we are performing on traditional relational databases and other NoSQL databases. But here we have certain advantages, and these are the advantages that we could perform for advanced application and the applications of the 21st century. So till then, keep learning and keep moving ahead. We will be learning more in the coming videos. Here in this lecture, we are going to learn about primary index. So let's start. The primary index is built on every cloud and database. This video shows you how to construct queries to access primary index through the API. The primary index API endpoint are called as all docs exist at the database level. You pass the HTTP verb get to the primary index to query without any query parameter. The output of primary index is a list of all the documents in the database, including the key and the value of the index. The key is the ID of the document. Index is automatically sorted by the key. The value will be a latest revision of the document. Here we see primary index for AnimalDB database. You can construct queries to manipulate the output of the primary index to retrieve a subset of documents based on their IDs. For example, you can retrieve a specific document using the key parameter. Here we have used the zebra. You can add include docs equals to true parameter to include the find document body, or you can use start key or end key to retrieve range of documents. Here we are using start key. You can also combine parameters to retrieve that the same range of documents sorted using the secondary parameter. You might be wondering why there is no uh, result when you are querying a view. Cloudent is like CouchDB, reads from the top, beginning at the start key, retrieves result through the end key sorted by the key. If you specify descending equals to true, the reading direction is reserved, so it reads from the bottom, beginning at the start key, and returns the result through end key sorted by the key. You can also limit the number of documents with limit parameter, or you can skip over the first two documents using the skip parameter. Here we have limited with a 3. The 3 output only will be displayed. The first 3 will be displayed on the screen. You can select any limitations and more. Similarly, you can skip the first 2 results or 4 results using the skip parameter. Keep learning and keep moving ahead. We will be learning more in the coming videos. Here in this lecture, we are going to learn about MapReduce, which is being implemented on IBM Cloud End with secondary indexes as analytical services with sum, count, average by making view. So let's start. Let us understand with map what is MapReduce. MapReduce consists of two phases, the map and reduce, which is used to sort a data. Currently, our data could be very huge or not very huge, but it is being jumbled. It is in a jumbled format where we have to arrange it in a proper manner. So the arrangement requires two phases. The map phase, which divides the data into various chunks or key tables. Then it has a reduce phase, which recombines those divided data uh, into a formatted alignment. It works with a divide and conquer methodology. Uh, it consists of two jobs, the map job and the reduce job. Map job works with under map phase, which takes a set of data and converts it into another set of data, where individual elements are broken down into tuples or key value pairs. And in reduce job, which takes place under the reduce phase, it takes the output from a map as input and combines those data into tuples of a smaller set of tuples. So let us understand how MapReduce works. Let us have a color diagram. We have data consisting of three colors that could have various occurrences and being jumbled into various formats. So we have various strips of data. We divide that data into certain sets. The set could be first set of dark color, then set of orange color, then set of yellow color. This is called a map phase. Then we have a shuffle of that data. Then after shuffling, we have the reduce phase, the combination of all the black color or the dark color as a single tuple, all the orange color in the second single tuple, and the yellow color as a separate single tuple, and all three are being combined after the reduce phase into a derived or differentiated data. Then here is another example. Here we have input data where occurrence of various words occur on the database. Suppose we want to perform the count operation of a CD keyword. We want to search whether how many times the CD keyword occurs in our table or in our database. We could perform count operation based on view or on analytics, and here we have the input data with certain keywords jumbled up in the database. We have to perform the map phase where the number of scores or occurrence of each keyword is being counted, and as a separate place. We have to take the Blu-ray and we have to point it one. Blu-ray occurred one times. Then whenever it against next time, we count again Blu-ray occurs one time, and then on the reduced phase we perform calculation the summation of all the values. We add all the occurrence of Blu-ray and print the display in the key value format with the key as Blu-ray and the value of the occurrence number of occurrence of that thing as the output data. Similarly, we could perform MapReduce in a huge range of scenarios. It is used with building up the secondary index on cloud and database. You can perform another analytical operations with MapReduce. It works with JavaScript and the Mongo style querying. You could perform that query to implement that concept. Welcome friends. Here in this lecture we are going to learn about secondary index. So let's start. Here we will create a secondary index and construct a queries to access the secondary index through the API. So before moving ahead, let us learn what is secondary index. If your query involves more than one lookup by the primary key, then you will need to build an index. Secondary indexes are built to wear the map reduce paradigm for analytics such as count, sum, average, and other things. The secondary index provides a way for you to query data. Here is the secondary index away. The secondary index allows you to provides a way to query data in more ways than just a simple primary key lookup. The secondary index is used to build using MapReduce paradigm. For learning about MapReduce, we have created another lecture on MapReduce. You can refer to that thing. The JavaScript function that defines the view are stored in a design document. During the map phase, the cloud scans the JSON document in the database. It emits the list of keys and values and build an index sorted by key. You can use if statements to restrict documents. This will be included and validate certain fields that exist. Then there comes a reduce phase, which is optional unless you want to do analytics on the values from the map. If you are only doing lookups that are based on a key or a range of keys, you can omit the reduce phase. There are typically four different examples that will show you the JavaScript portion of the map that are used to build the indexes which get inserted into the map field in the design document. The first field is a feed by user that returns documents sorted by user ID. Then there is a feed by user time taken. Uh, Here you have to notice that the key that is emitted in the map can be more. The key is an array of both the user ID field and the time taken. Since the indexes are automatically sorted by the key, it sorts first on the user ID, then on the time taken. Here we have all the JavaScript function for all the categories. Then there comes the count by user with example which builds the map sorted by user ID and then reduce it by country, counting the number of documents returned and total sales by person, which builds the map where key is the name of the salesperson and the sales amount which is summed in the reduce phase. Whenever possible, use the built-in reduce of count, sum, and stats. They are natively compiled in Erlang, the language of CouchDB, and the database core of Cloudend, and build a query much faster than the certain reduce cases. Now, after there, we are going to provide a practical example for building the secondary index. Let's start with the practical. You can create a view by placing the map function in optional reduce function in the design document in the database. As soon as the design document is saved, the index is to start building. Here you see the dashboard and the utility to build both the view of the JavaScript functions that make up the map reduce. You can use the dashboard to create a new index, edit an existing one, or query the index. This example shows a count by user new in the design app in the found by database. The index emits the user ID field from the document as the key for the index and null as the value. The reduce closes the reduce as a count when a second parameter of the emit function is null. Cloudent like a CouchDB then only stores the key and document ID in the view. You can use the view as a compact lookup mechanism and fetch the document details if needed in subsequent request or by adding the parameters doc equals to true. Indexes are built at the database level, and so the query and index you include the database in the URI along with the name of the design document that contains the index. Then you specify the view for the secondary index and map reduce and then the view name itself. Alternatively, you can use database dashboard curl or the browser plugin like Postman or REST client to query the API in the same way. Here we have various views like count by user, count by location, count by date, count by time, and other things. Similarly, we could create multiple cases. There are a few additional parameters that are specific to a secondary index. The stale speeds up the response. Here we have a stale parameter which speeds up the response as it doesn't wait for the index build process to complete. Then the reduce equals to false parameter which turns the reduce off by default. It is true. When you add reduce equals to false, the result of the map is shown with the emit having the key of the user ID and value being null. The group equals to true parameter groups the result by unique key. Here user ID, the value is reduced via the count function to show the total number of found bytes per user. It's only valid when reduce is turned on. By default, group equals to false. So this was about a secondary index. We are going to learn more in the coming videos. Welcome back friends. Here in this lecture we are going to learn about Cloud and Query and get an overview of the same. So let's start. Cloud and Query provides you a clear declarative way to define and query indexes, the primary index, secondary index, the search index and more. Here you are going to learn concept of Cloud and Query, which is a larger logical starting point for developers new to Cloud and Apache CouchDB. And for developers who are familiar with SQL, Cloud and Query is also easy to learn and use. The JSON object, here we have two objects here. The JSON object on the left defines the new index and the JSON object on the right is an example of a request body to find docs using that index. In the right side, we have selectors, the person name, movie year. It is similar to Mongo style query. And on the left side, we have indexes and fields. The two new API endpoints include the index and find, underscore index and underscore find. The underscore index is used to manage the indexes, and underscore find is used to execute queries against the Cloud. Instead of using JavaScript functions to create an index with Cloud and Query, you define an index by posting JSON text listing the fields you want to index. Indexes are implemented behind the scenes as either a primary index, a secondary index, or search index. Here you see a comparison of equivalent queries using SQL, MongoDB, and Cloud. The Cloudent example is using a secondary index using MapReduce. The query shows how to find all views between at the ages of 25 and 50. Then there comes the Cloudent query example. Here we have the curl example. With Cloud and Query, you would use the syntax shown here to query all users between the ages of 25 and 50 instead of the view syntax seen previously. Here we are not using the view syntax. Then there is the typical two types of declaration, the type JSON and the type text. Here are advantages to use each type of Cloud and Query indexes. Using the JSON type leverages the map phase of MapReduce and building a query faster than a text type or fixed key. But this type of index restricts the operators you can use as a basis for query in a selector and might end up doing more work in memory for complex queries. Using the Cloud and Query text type index, which leverages the Lucene search index under the covers, it prevents the indexing of all fields and documents automatically with a single simple command. It also provides more flexibility to perform ad hoc queries, sort across multiple keys, and permits you to use an operator as a basis for query in the selector. Here we have a selector syntax that can be used to express conditional logic using specially named fields. If you're familiar with MongoDB querying, then this seems similar. A simple selector might match any document with the name Paul. The extended selector would match with a name corresponding to a particular location. It could match multiple values. Similarly, if we have subfield, which is differentiated with a period symbol, suppose we have a location. In location, we can have multiple arguments like city, state, and other things. That is denoted with a period symbol. Then we have operators, similarly for age and more things. Here we can use a greater than symbol, a smaller than. The greater than is represented with a dollar $GT sign, and the smaller than with a dollar SM sign, ST sign, the smaller than. Then there are two core types of operator in the selector syntax, the combination operator and the conditional operator. A condition operator checks for a specific condition to be true. A combination operators are used to combine conditions or to create combinations of conditions into one selector. They take a single argument, either a selector or an empty array of selectors for the combination. Here you use the allowable combination operator. The conditional operator goes similarly, which are specified on a per field basis and applied to the value index for that field. Here you can see the allowable conditional operator condition operator. And here is a sort key or sort, which is an array of a field name and direction in ascending order. For JSON, one of the fields must appear as the part of the selector and all sorting fields must be indexed. As text type, sort as shown here. You can use the text method and below or the JSON format as above. So this was about Cloud and Query. We have learned about Cloud and Query. Similarly, we could implement certain logics with primary key, secondary index, and Cloud and Query. Try implementing your own database and integrate it with other solutions.
We have explored storage and compute services of Amazon Cloud, and now here we are going to start with database services. So what are the database services available on Amazon Cloud? We are going to learn and explore. So database services comes in two category: self-managed and managed services. Self-managed services are the services that you are you as a developer or customer are expected to be managing. But managed database services are the services that are primarily managed by Amazon. So why managed database services are used? Typically, when you host your database on premise or on your own data center, physical data center, not on cloud, then you need to manage everything from physical hardware network, rack or stack, to app optimization, scaling, and everything. Yeah, app installation, be it by app installation, upgradation, physical maintenance, database patches, OS patches, everything. You need to hire a DBA, database administrator, you need to hire a network engineer on occasional basis, you need a continuous supply of internet, you need to maintain physical hardware, and if hardware got outdated, you need to upgrade our scalability factors. But when you use database on premise, sometimes managed, you can shift those managed services to Amazon Web Services. The physical or hardware part or network part is managed by Amazon automatically. Uh, However, rest all other things are managed by you, be it with software or database patches. But when you host your Amazon database service on EC2, you also get another option where you just need to optimize your app, provide data sets, or your rules or your services, whatever you define, your application. You just need to code or test or deploy, nothing else. Everything from scaling to database backup to software patches, OS installations, and network वगैरह, all are managed by AWS service. So what is the difference between self-managed service or AWS managed service that are offered on AWS cloud? When you go with self-managed database, when you want to manage everything from of database and everything, you have full responsibility for upgrades and backup. You have full responsibility for security. If there is any security breach related to database aspect or software functionality, that is your concern. Full control over parameter of servers, OS, and database. The replication is quite expensive for you, complex, and requires a lot of engineering. You need to know everything. You had to be supposed to be an expert when you go with self-managed database. If you are expert and knows everything better than a normal guy, you can go with self-managed database. But you are not such a specialized person, you must go with AWS managed databases that provides upgrade, backup, and failover as a service from their side. You don't need to worry about everything from infrastructure to security to certifications. You give tools to ensure database security data that are managed by AWS team. Database is managed appliance, so you can easily automate. AWS providers failover as a package service. They also provide failover as a package service to you. You can test your applications. So these are the four major services that are provided with database category: Amazon DynamoDB, Amazon RDS, Relational Database Service, Amazon Elastic Cache, and Amazon Redshift. We will explore each of them one by one in a detailed manner. Amazon DynamoDB is a document and key value store database. RDS is SQL database engines that could consist of other relational databases like MySQL, Postgres, Oracle, and various other databases. Elastic Cache is similar to cache memory of your desktop. It has a strong memory cache when you need for certain scenarios like game development. And Redshift is data warehouse service. So keep learning, keep moving ahead. We will learn each of them in the coming videos. So friends, we have explored other services of Amazon. Now we are going to explore Elastic Cache. It is not a database actually, but it is an in-memory cache which is very fast because it is cache memory. The data kept in Elastic Cache is usually in a high demand and must require a high speed. That data is kept in Elastic Cache. It is also a middle layer in between the web browser and a storage. It improves performance of applications. Speed your applications by bypassing database access and disk storage. Elastic Cache is used for high speed data access. For example, if you have created a website where a person is supposed to log in with his credentials and then retrieve all the resources from that database. But if your website requires multiple time of login, then retrieval and verifying all the times from the original database is a tough job. If you can store some of the credentials or hashes in Elastic Cache, it would be better and easier for you to do so. It supports two types of engines, memory cached and Redis. You can use either of the two. The Redis is very fast, rapid, and it is highly integrated. We would explore it in the coming slides. And memory cached. So how we can integrate build a solution? This is a typical use case for Elastic Cache. We can integrate other solutions like DynamoDB, AWS Lambda in virtual private cloud or API gateway. This is a scenario where, for example, get session is started, get request is made from the API gateway or from the web browser which is passed through the API gateway to a specific function that is stored on AWS Lambda. The Lambda functions could be setup stations function, stream processor function, and list stations function in this case. The first request is sent to setup station function. Then that function is called and some operations on the database DynamoDB, that is NoSQL database, or you can say replace it with RDS or any other form of database. The function, a lambda function is called, some operations is performed on the database or datasets, retrieved or verified, that could be login or other form of things, which then generates a stream, DynamoDB stream, and triggers another lambda function, that is the stream processor function, which then triggers Elastic Cache. It fetches some information from Elastic Cache which was in the backend fetching from other database or other storage like S3, which can also be directly triggered by another script, that is list stations function. This is a typical scenario that a cloud architect is going to devise. Let's study another scenario. This is suppose as we have learned earlier, you can also host a static website using S3 storage. You just need to upload some files, HTML, CSS or JavaScript files online, and you just generate a file name for index file, and you just click on the link address to that file, and it will open up. So how it could be better work in an integrated environment with using multiple AWS services. So let us see a typical example. We have hosted our website in S3 actually. So this is at the bottom right side, the red one, Amazon S3. This is dynamic content and the above one is static content. For example, if we want to uh, open up our website, a browser made a request from any remote location throughout the world to open this website. He has the URL which is directed to the AWS CloudFront distribution and checks whether this website exists or not. If it exists, it searches to an S3 storage, and provides the link and the page available to the web browser directly. Here we made use of two services, Amazon CloudFront Distribution and Amazon S3. In S3, HTML, JavaScript or CSS static content was kept. Another scenario where we want to provide dynamic website, we can use another solution where some of our content is kept in S3, some of our data is kept in DynamoDB or RDS or other form of database, and we have certain scripts that are serverless or Lambda functions that are kept in Lambda. And we have elastic cache where some uh, vital information that are required multiple times used to be kept in elastic cache. So this is an integrated solution where we can employ multiple types of databases as well as storage options as well as Lambda functions with elastic cache. Here when a browser make a request to open a certain website, it goes to Amazon API gateway, passes through the virtual private cloud where your application resides. It triggers a Lambda function that may call Amazon DynamoDB, fetch some information from DynamoDB, fetch or write some information to or from RDS, Relational Database Service, using any kind of database, MySQL, Postgres, SQL Server, or other things. Um, Fetch or write some information using Amazon Elastic Cache that we are exploring right now, and with some login credentials that may require IAM authentication to Amazon S3. Now we can use Elastic Cache for Redis. So let us explore what is Redis. Redis is an option for Elastic Cache. It has a managed service, use existing clients, pay as you go is available here. It is available in all public AWS region at launch. It is not available at US Secret or US Government Cloud because we can't host a website in anything in that region. That is restricted to some common users. So Redis is not very typical thing where it is a simple solution using Elastic Cache. When you create an instance of Elastic Cache, you have an option to create a Redis. You can use Redis to accelerate your application. It automatically makes use of elastic load balancing, EC2 application instances, app reads, cache. You can use cache memory. It is simply cache for database or any kinds of reach. We can use it in other scenario, the elastic cache. For example, we want to develop an IoT solution using cloud. Here we make use of multiple AWS services. For example, certain event is being triggered by any AWS IoT device, which is authenticated or reflected by AWS IoT service, fetched by that service, recorded by that service, hosted on cloud based on certain domain and login by that device, which may trigger any AWS Lambda function, Lambda code, the serverless code, which may trigger, which may require access to Elastic Cache or some data, which is fetched from EC2 Elastic Compute Cloud or computed on that behalf and reflected back to Elastic Cache. Elastic Cache then provides the data back to AWS Lambda script, and Lambda script performs certain types of operation. We can devise a data. In another case, this is other use case where our IoT device creates a Lambda request. The Lambda function calls when the data is very hot or very specific, very highly required. We can make use of Elastic Cache, or if it is not highly required, very hot data, we can use a longer retention and store the information in DynamoDB or RDS. Or when the data is very less useful, or the size of data is very large or quantity is very large, and we could not afford elastic cache in that scenario, or actually does not need that data. We can store in the vault or warehouse, either in Glacier or Amazon S3, using Amazon Kinesis Firehouse. We can also capture data using Redis. This is another use case similar to that thing. We can capture or do analysis work. Big data analysis is a popular term. If we have an information about a site or certain kind of data application, we could do analysis using Amazon Kinesis streams from the data source and store in either of the format. If it is hot data, we can move to Amazon Elastic Cache, either using Redis or without using Redis. If it has longer retention, we may use RDS or DynamoDB, or when it is not useful at all in real time, we can uh, store it at cold vault. So this was Elastic Cache. We can make complex applications or solutions using Elastic Cache. So keep learning, keep moving ahead, keep building a solution.
Now we are going to create an instance for Amazon Elastic Cache, which you could find from navigating through the dashboard of AWS Cloud. Move to the database category, select Elastic Cache option. Here you can create in-cache memory or manage Elastic Cache instances. So this is the dashboard for Elastic Cache, which is a web service that makes it easier to launch, manage, and scale a distributed in-memory cache for the cloud. You can launch a cluster, connect to the cluster, and manage through the management console. So hit the get it started now option. Here you have cluster engine options, the memcached, memory cached, which is a high performance or Redis cache. You have to provide a name for the settings for the configuration. Provide any name, whatever you like. You can also choose from the cluster mode enabled or disabled. You can provide a description that is alternative. You can provide the engine version compatibility or the port number through which it will connect, the parameter group, the node type. Node type could be large, small, anything like that, and number of replicas. For advanced settings, you could go to the subnet groups, provide a name. For you can also attach a virtual private group, virtual private cloud VPC, provide an ID for VPC, and provide the subnets associated with the virtual private cloud. You can choose from the preferred availability zones. If you choose no preference, it will automatically be installed anywhere in the world in any AWS region, or you can select the zones like EU West, US East, Singapore, Mumbai, anything like that. Then you can select import data to clusters or create the backups, the seed ID, RDB file S3 location. You can enable a retention period, the maintenance, and hit the create button when you are configured for these things. You can also set SNS notifications that could be integrated with Amazon Pinpoint in the mobile app categories. And here it is showing creating, the status is creating. When it is created, it is to show in the green color. The node type, the shreds, node, and everything which is showing here. You can go through the options that is available on the left hand side. You can choose from the backups, the reserved nodes, the parameter groups, the subnet groups, events, Elastic Cache cluster client, and more. You can always create multiple cache systems. To create a client, you have to choose the version for PHP, .NET, anything like that. Because it is a web service, you have to call it from any programming language, that is backend web development language, through which you have to create a page. So there are various options available here.
Here comes Amazon DynamoDB, that is predictable and scalable NoSQL data store or database. You can store a data set or your data in key value format or in document oriented database with Amazon DynamoDB. So now let us explore what is DynamoDB. DynamoDB is a fully managed proprietary NoSQL database service. It is not a relational kind of database. It can be integrated with Hadoop via Elastic MapReduce. The languages frameworks that are supported with DynamoDB to be programmed are Java, Node.js, Go, C Sharp, .NET, Perl, PHP, Python, Ruby, Haskell, and Erlang, or the new form of Erlang programming language, that is Elixir. They are supported on DynamoDB. DynamoDB is fast, consistent performance, single digit millisecond latency, very less latent. As it is document oriented, it is highly scalable and can handle uh, a large number of requests simultaneously. You roughly need zero administration when you go with DynamoDB. So how it works consists of, it basically consists of AWS SDK, that is two types of thing: DynamoDB Web API and DynamoDB Streams Web API. It consists of two fundamental entities: the DynamoDB where your data is stored, and DynamoDB streams that are used to call your application or flow in a catch form. So they interact with your application in the fashion your application sends API request or API calls to SDK, DynamoDB Web API, and streams. First, the DynamoDB Web API is called, it returns a request, then DynamoDB Streams is called, and it returns the request, and your operation is continued. Let us test a use case for this. For example, if you want to do some malware analysis, you can implement a solution like this using multiple Amazon services like DynamoDB or AWS Lambda. So how it works? In your DynamoDB, you have two large set of data sets are stored. That is malware catalog and event store, where you store the details of a malwares and events. The first thing that happens in your system is that a threat uh, intel with malware hashes are recognized with threat intelligence script or concepts which are verified or recorded on the malware catalog stored in DynamoDB, which is being upgraded. Then the malware catalog is report the sensors of various devices, report software installation events based on that malware hashes. Then DynamoDB creates a streams of data that triggers Lambda, where your script, serverless script for uh, your applications like push notification and other things are stored. Then Lambda compares against known malware hashes that map a new hash is compared to known hashes, and when it is compared, it publish alert upon match using SNS and sends notification, email, mobile, web app notification, any kind of notification to the uh, assigned responsible authorities. This way you can manage a software, or for example, this is a use case for an antivirus firm that can recognize a new kind of virus or malware. You can build a large number of solutions. This is another use case for DynamoDB. Here we have integrated multiple solutions, that is Amazon IoT, DynamoDB, and API Gateway. We have developed an IoT application where a user triggers when IoT event is triggered, for example, a button click. Then AWS IoT, which integrates your IoT device hosted on internet and triggers an Python script via AWS Lambda. The script uses certain content stored on your DynamoDB database, which can trigger another Python script or any other language script or simple functions via Amazon API Gateway, and your RESTful stats can be generated. So this was DynamoDB. It is similar to MongoDB or other NoSQL document-oriented database. You can give it a try. Your data is stored in a JSON format, key value pair. The documents you can also store in CSV format or simple text formats, but your data must be in key value format. You can check out more details and build a solution. Here comes Amazon RDS or Relational Database Service. We are going to explore it right here. So RDS is Managed Relational Database Services that comes with multiple relational database service options. That is Oracle, Microsoft SQL Server, and other things, other databases. So what is RDS? Basically, it is simple and fast to deploy. It is a relational database where you can create tables, databases, create a schema, run SQL queries, and run other backend scripts like PHP and other scripts that run SQL query. You can store your data, retrieve your data, and do all the operations that you can do with any traditional SQL based database that comes with Amazon RDS. AWS handles patching, backup, and replication. It is compatible with your application. Choose among the available databases. The Amazon has its own database, that is Aurora, and the new one is MariaDB. It is fast, predictable performance. You only pay for what you consume. That means pay as you go. No initialization cost. Amazon Relational Database Service consists of multiple solutions where you can have choice of database engines, managed services, easy to scale and operate, high performance, and high availability. So these are the services or database options that you get: MariaDB, Amazon Aurora, Oracle, Microsoft SQL Server, PostgreSQL, and MySQL. You can also create multiple databases at same time of different vendors and build an integrated solution almost in minutes of time. What you can do with these databases, you can read replicas, customize performance, create automated backups. The backup, you don't need to create replication or shredding, that is automatically done here. You can integrate IAM authentication to drive other developers or testers or your team to access the database services. It is cost effective, highly available, and you can integrate monitoring tools like CloudWatch or other things to monitor the resources and everything that is used.
Now we are going to create an instance for Amazon RDS or Relational Database Service, which could be found under the database category on Amazon dashboard. So hit this option, the RDS. Here you have a plenty of options available. You can choose from instances, cluster, the performance insight. You can get a snapshot, the reserved instance, and more. The simple way here you have launched dash database instance option, which you could create a database and you can restore from S3. Here are the benefits, the use cases available in the first page, the starter page of this RDS. And when you create a database, you have to choose some different options. You have various pricing plan, the free tier, and more. You can choose from MySQL, Aurora, PostgreSQL, MariaDB, all the traditional relational database systems. These are the engine options available here. You can choose from Aurora, MySQL, MariaDB, PostgreSQL, Oracle, Microsoft SQL Server. Let us select anyone from this and choose the next option. You have different capabilities available with different types of engines, database engines, and based on a requirement, you can select that thing. And obviously, you can create multiple database instance at the same time. Suppose your application need a MySQL database as well as SQL Server, you could choose to create both of them simultaneously. You have to specify the database details. You have to choose from the versions, the database licenses, uh, and so on. You have to create the class for this, say micro with one CPU and 1 GB RAM. You have to allocate the minimum storage capability. Uh, you have to provide the database identifier. Uh, the minimum capability should be at least 20 GB. So initialize it with 20 GB. Select the database identifier, instance identifier, the unique name for this. Then you have to choose from the master username, the password to access the database that is stored in the configuration files. Let them provide anything. You can provide any value with alphanumeric characters. You can choose from a letter, a numbers. Try to choose a strong password so your database may be safe. Then hit the next button. You have configuration options available here. You have to choose the network and security options, the VPC, virtual private cloud, if you include. You can choose from the subnet groups, the default, or you can omit this thing. You can create a new VPC client group, or you have to create a database name, provide a name for this database after initializing the engine. You have to select the port number, the virtual port number, like SCS 8080, 8090, and so on. You can choose from enable IAM database authentication, the disable option. You can access with IAM. You can select the backup window, say 7 days, a month, or more. You can enable the monitoring options or disable monitoring. You can create a log file export for a purpose, the error, other files. You can choose from the maintenance option, enable auto minor version upgrade or disable auto minor version upgrade. You can select the maintenance window based on the requirement, and you can view the log files, the error, and other details in the CloudWatch. So you have to create a database based on your selection. Hit the create button, and if you have any doubt, you can always recreate it. We have created our database, so it is loading. So it is here. It has a free space, no pending IOPS, and anything operation, no operation yet. So the matrix is not showing anything. When it is performing, the matrix is being displayed on the screen. Here are various options. You can choose from the different preferences. You can always change. Uh, Keep this thing in mind, the ARN, which is very important thing. If you want to integrate with other services, you have to use this ARN to uniquely identify this database instance on the Amazon resource. Here we have our database. You can store the database from S3 storage or other options. Welcome back, friends. We are learning AWS databases, and here we are going to learn about Amazon Neptune, which is a graph database. So let's start. Graph database are very useful these days. We have relational databases, NoSQL databases, new SQL databases, document-oriented, column-oriented, and different kinds of databases out there. So we need a graph database if we have a huge chunk of data and there is a relation between multiple entities at the same time and some sort of data that could not be stored or uh, fetched easily from traditional databases. Here we have graph databases for various reasons like social media and more things. So we are going to learn about Amazon Neptune, how we can leverage the power of Neptune here. So it is covered as a tool for using social networking, a recommendation engine, fraud detection, knowledge graphs, life sciences, network and IT operations, and more use cases. It could be implemented with other Amazon services like VPN, virtual private network, and more things. We have the pricing plan, which is based on on-demand storage, I/O backup, and data transfer, and it is represented using nodes and edges. So this is a graph, simple thing. It is a fast, reliable graph database that makes it easy to build and run applications that work with highly connected datasets. Here we have datasets. Datasets are represented using nodes, as we have in a graph. In data structure, you might have read sometime that there are nodes, the graphs. We have different types of algorithms that work upon the graph. Simply, we are implementing the data storage on that kind of graph. There could be tree structures or graphs. So here it is. It is a simple graph database, a representation of a graph. Here with the circles that represent nodes or data sets, which are connected with some other data sets or nodes using edges or relations that could be used. So here we may have different kinds of graphs. Google search algorithms also work on graph. The page rank is governed using the graph algorithms. For example, if your website is being linked by certain popular sites or a wide number of sites, it will be backlinked with other graphs, other nodes. And when a certain site or certain web page is being linked with multiple other sites, it will be weighted more. So when a person type, say, coffee in New York, and you are a store selling coffee in New York, then your store will be ranked higher than others if you have higher backlinks or number of links. Here on the left hand side, there is a node which is connected by maximum number of other nodes. So it will be weighted more as compared to other nodes if they are dealing with the same content. Otherwise, for different content, they would be weighted differently. Similarly, here is a typical example that could be used with a graph database. Here it is an example of different relations that exist together in a graph. So here we have a Eiffel Tower as a node, which is a place, a relation is place, which is being visited by Bill, Alice, and Bill is a person and Alice is also a person. So here we have nodes, Bill, place, Alice, and Eiffel Tower, and here we have relations or edges, which is represented by a function called visited, visit, is a, and so on. Eiffel Tower is also located in Paris, which is also a node, and Paris is a city. Here we have these things. Then the other could be Bob, which is a friend of Alice, and which is also a person, but not a friend of Bill, as there is no direct relation. He may be a friend, but here it is not represented, so we assume that he is not a friend. He is interested in Mona Lisa painting. He was born on a certain date, and Mona Lisa was created by Leonardo da Vinci. This could be an example of a graph database. Here it works. We may have a data sets in certain format that could be represented. This is a typical example of we can have a complex or very highly complex data. Facebook or other social network sites use these graph databases to empower their site. If you're thinking or planning to build a social network or other things similar to Facebook, you could be using Amazon Neptune at some point of time to implement this graph database. Here we have another use case for genetic algorithm or disease medical treatment. We may have different scenarios here. We have a node called disease, which is associated with another node called gene. Gene is associated is a part of a pathway. Pathway is a part of gene. Gene is a part of pathway, and so. A protein, a medical subject healing heading is a node which is classified by a disease, which is again associated with a gene. So we may have a same node repeated multiple times, but could be represented or a part of different nodes. We don't need to be having a graph which is a two-dimensional. We may have a multi-dimensional graph, not just three-dimensional, four-dimensional. It could not be visualized by any of the model of that we have. The Facebook relations are not two-dimensional or three-dimensional. They are multi-dimensional. We could not define that it would be four-dimension or five-dimension. The spatial dimensions is not very relevant. They could be overlapped and could not be simply represented by a graph. There could be multiple graphs existing parallelly. Here it is another graph for a media network or a inventory purchase. You may have a shopping site or e-commerce site. You may have a person who is purchasing something from your site. He may be interested. How Amazon or Flipkart or other Alibaba or other e-commerce recommendation engine works. You might have observed that when you visit a site, you visit an Amazon.com site and you just simply search for a trimmer or a mobile phone. And when you are not interested or you did not purchase even or seen for a certain, say, iPhone X, and after a few days later on, when you don't visit Amazon site or did not place any order for that phone, they will send you ads, advertisements, or messages or notifications to allowing you to redeem an offer that is made on this product. Uh, how the Amazon know that you are interested in that product or they recommend you these things. It is being used with the graph or at a certain point of time. We don't even know what we need to buy, but Amazon may recommend us that you may be interested in this product. They observe our pattern, they observe the pattern of our friends and associated ones, and they follow the order. They could recommend us things that we may plan in future to purchase. This way, the recommendation engine works, and everything is powered with the graph databases on the cloud. Here are huge benefits of using a graph database or a Neptune GraphDB because it supports an Open Graph API, which could be integrated with Kremlin, SparkQL, and different kind of things. It provides high performance for both of these graph models and their query languages. Supports multiple query languages. It lets you choose the property graph model and its open source query language, Apache Tinkerpop, Gremlin, or W3C standard research description framework, and more. It has a high performance and scalability. It is a purpose-built high-performance graph database. Could be optimized for different queries. It supports up to 15 low latency read replicas across different availability zones to scale and read the capacity. It is scalable because it is on cloud. You could scale up anytime you want. It has a high availability and durability, 99.99% uptime, which is available. So it follows the fault tolerance and self-healing storage build. So you don't need to worry about the networking and other issues. It is highly secure, and if you are in a doubt, you can use the VPC and encryption or other sort of things like guard duty and different services offered by Amazon Cloud to keep it more secure. It is fully managed, so you don't need to worry about a database management tasks such as hardware provisioning, software patching, setups, configuration, or backups. You don't need to worry about the new package or update that is being made on the Neptune. It will be automatically managed by Amazon team. You only need to provide a database and perform the operations, whatever is required for your business domain and other purpose. It could be research or learning purpose. It works in a different scenario. We have to first load the property graph and RDF data, uh, the resource description framework graph model, and, and provide it by the S3, Amazon S3 storage. Uh, we may have a property graph or in the CSV, comma separated value format. We may have a resource description framework having a total n triples n quads or RDF or XML format of data. Then we have a bulk load API to store billions of relationships that could be stored in the S3 or other sort of database that we have on cloud. Then we have fast graph queries that could be performed on this data that is stored with RDF graph or having a billions of relationships. You may have a Spark QL endpoint or Gremlin server for executing, building and running applications to query a large chunk of formatted data or perform various kind of analytics work on these things. So when we use the graph database, if there are various use cases. We may have a social networking site, there may be two-person who like certain things or did not like certain things. They may be friend, they may connect to a device, they may have read a certain books, watch certain movie, play certain game. They may have check-in at certain places, a location, hotels, use certain services, and more. We have this database existing. Then we have a recommendation engine that we have learned about with the Amazon example. Then we may have a fraud detection that could be used for OTP and different kind of things with a credit card system or other financial estimates. We may have a purchase transaction in real time to easily detect fraud patterns. Suppose that there is a known fraud which may use the same email address and paid with the same credit card. So when you approve a purchase, a product, there may be OTP or different kind of things that could be implemented with graph queries, and that may identify different kind of frauds. So you may be nearly secure with a certain kind of frauds. Then we may have a knowledge graph storing different kinds of data. which may have a huge chunk, and we may have a uh, which may have a relationship and huge data. Similarly, as our brain stores the data, it implements a knowledge graph, and there are certain relations linked with other certain relationships, and there will be more and more data and relations out there. We have a huge data on Wikipedia, and which could be implemented with Wikidata and different things. You may be a genetic researcher or a particle accelerator engineer, and there would be thousands of subatomic particles or uh, millions of genetic data. So it is very hard for a human to detect the behavior of a single gene or single pattern. We may have a knowledge graph and keep computers to compute and decide what the pattern, observe the pattern. We may simply analyze a certain segment. We don't need to analyze everything. So that's the use of knowledge graphs. Then we could use it in life sciences. We could use it with network and IT operations for different kinds of IT operations. So for packet sub routing on the network, the subnet mask, and different packets that we have. We may work with a peer-to-peer network. These days we have a blockchain technology out there. We could empower a GraphDB with a blockchain and different scenarios as well. We may have a cryptographic hash or different files sending out there, and we may have need a GraphDB for those packet arrival and sending things. It could be Amazon Neptune could be deployed with a VPC in a secure environment to increase the availability through our deployment into subnet zone. We have a cluster volume always span different availability zones to provide durable engines, and we may have set up and integrated with different internet gateways, storage gateways, and different services. It could be integrated with other things, other cloud services as well. We may have different scenarios. This is a simple use case where we have a storage bucket that is being authenticated using an IAM role by the Neptune instance, which stores the data back and fetches from this SA to the Neptune instance, the graph data, which is being uh, recommended by a client. The client copies data to the bucket and then loads the command and execute on the Amazon instance. And Amazon instance and S3 is being performing a task, authenticating using the IAM role. Then we have different graph models and frameworks. The Gremlin traversal language for property graph and RDF resource description framework with Spark QL query language. There is more use cases with AppSync, a recommendation engine that could be used with Amazon Cognito and different kind of things. So this was a brief introduction about Neptune DB. We can implement a huge and complex solutions with this graph databases. So try giving it a trial, uh, give it a trial and try to build your own solution. Hi friends, now we are going to create an instance for Neptune DB that is a graph database on Amazon Cloud. You could navigate through the Amazon Cloud dashboard, and here you can find the Neptune option in the database category from where you can create a graph database with Neptune. So hit that button. If you have an existing Neptune database, it will appear on your screen at first. Otherwise, the getting started page will appear like this. You can create a reliable graph database that is fast. It could be useful in various scenarios. You can check sample use cases from the getting started page or hit the launch Amazon Neptune to create a Neptune database. Here you have to specify various things. You have to define the database engine version for Neptune. You have to select anything. You have to select a class for large based on CPU usage or RAM. You have to define the configuration. You have to define whether to create a read replica in different zone or not. You have to provide a name for identifier of this database. You could choose any alphanumeric character with hyphens or with characters, different conditions. Just provide any name, unique name. After you have provided these things, hit the next option. Then you have to configure the network and security options. If you have a VPC, you have to provide it here. You can choose from a default subnet group or create your own. You can choose availability zone from different zones available here. You can create a VPC virtual private cloud security groups, or you could use the default. Then again provide the identifier for cluster name, define the database port for communicating with applications, then provide the database parameter group, the cluster parameter groups. Then if you have an IAM database authentication, the identity and access management role for different users, you could choose it. Otherwise, you could disable it. You could choose from encryption or you could not. You could omit this step. You can select the priority for failover or automatic backup. You could choose from the maintenance option. Uh, and if you choose the backup, you have to choose the window for weekly backup, daily backup at particular time, for duration. You can set it at the first phase as well. You could also select this afterwards. If you want to change, you can go through the settings. Otherwise, you can create a new instance. Obviously, you can create multiple instances of Neptune. If it exceeds the free tier limit, you could pay as you go based on the requirement. Here are the instances that are being created. The status is showing creating. You could choose from snapshots. You could create a snapshot. Always configure the subnet groups and other parameters. Here you have the ARN, which is very important if you want to integrate it. Keep this in mind. You could copy it anytime. Just you have to, it is a kind of credential that you have to associate with other services. So it is being created. The status is showing green, available. You can find all the configurations here. You could perform various actions. The associated ARN is useful. Amazon resource name. Here you have cluster endpoints that you could use for navigation purpose with other applications. You could use a resource ID. These are all available here. Here we have different options that we have configured being displayed. After our Neptune graph database has been created and is available, we can choose various options. We could set different metrics. Um, so here it will show when you choose any option. We have chosen an instance of Neptune DB. It is showing the CPU utilization, the current utilization rate, the engine uptime, the free memory, network receive throughput, and different metrics. It is showing the port number, the public accessibility. It is showing no. You have to change it if you want to create a web service or other things like that. If you want to allow Neptune database on the access to a website or other applications, which is being made public, you have to choose that public options. You could create a snapshot by hitting the take a snapshot option here. You could add different tags For Neptune database, to organize and track your Neptune cost so that it may not exceed a particular limit. You could write the logs on the CloudWatch where you can find the errors and check different log entries and different things like that. And similarly, we could set other permissions. We could check different monitoring graph metrics. We could choose from the instance action, create a read replica or point of time, and stuff like that. And you could create multiple databases anytime you want.
So let us now explore Amazon Redshift, which is another in the database category, but it is not actually a database. It is a columnar relational data warehouse. It is a data warehouse where a large chunk of data, larger than the database, is usually kept and stored. Let me tell you a simple example for those who don't know the difference between database and data warehouse, which information is kept in database and which is kept in data warehouse. You may have booked a railway ticket, train ticket, metro ticket, or aeroplane ticket online. So think from the perspective of the airline agency. When somebody or a large number of people book their tickets for a particular flight, suppose let's say British Airways carries over 1000 flights per day from different locations across the world. So for each flight, almost 1000 persons or 500 people, for example 500 people, book their tickets online. They book ticket in advance, usually 1 or 2 months ago. For example, they booked a flight ticket for 22nd October 2018. Till 22nd October, the information of the people who will travel through a flight will be kept in a database. When the data is hugely required, you can perform query, validation, and other forms of data operations. After 22nd of October, when the flight has landed those people, the data is not actually deleted, but it is shifted to a data warehouse. A data which is not being used right now, but can be used in a near future for any sort of thing. For example, if the plane crashes, so there is a problem for insurance claims. So how can the airlines industry verifies who were boarding on the flight? If they have to maintain everything on a database, the database will soon degrade because there are 1000 flights every day and they have to list details of 500 passengers each day. Such a huge challenge to a database. So all the data which is not in current use is stored in the data warehouse. So Redshift is a typical solution. So now let us explore what is Redshift. Redshift is a columnar relational data warehouse. It is massively parallel. It can perform parallel processing. The data that can be stored here is of the scale of petabytes. The charges for your storage is up to $1000 per terabyte per year. So it is cheap as compared to other solutions. You can use existing business intelligence tools like Tableau and other tools along with Redshift. It is based on PostgreSQL, so it is relational and you can perform SQL queries and operations. So this is a simple architecture for Redshift. It has a leader node, the compute node, and everything is mirrored. The leader node manages the compute nodes who perform columnar storage and execute queries in parallel slices, either via S3 or other sort of storage. The leader node performed is based on Postgres, stores metadata about compute nodes. It can communicate with clients using business intelligence tools and other things. It helps coordinate query execution. So this is a simple scenario where the difference between traditional data warehouse and Amazon Redshift. In traditional data warehouse, you require a large number of team to manage your data warehouse. You need to maintain physical facility, network engineers, database administrators, and other sort of developers. But with Redshift, you don't need to worry about all sort of things. Everything is in cloud and managed by the cloud vendor. You just need to upload your data or download or retrieve or just forget about it data. Redshift work with existing business intelligence tools. The tools could be Activate, Burst, Jaspersoft, JReport, MicroStrategy, Pervasive, Tableau, and more. They can interact with Amazon Redshift using JDBC or ODBC bridge, ODBC JDBC driver for languages like Java, C, and other. Connect using drivers from Postgres SQL and other things. This is a typical scenario where we can integrate a solution with Redshift and S3. For example, we have currently a corporate data center where a huge chunk of corporate data is stored in data warehouse, and suddenly our company start feeling that we should migrate our data on the cloud. So how we can do so? We will define the schema conversion tool, establish certain migration agents, then the migration agents pass our data to Amazon S3 bucket, that is object storage, and after your data is passed to S3 bucket, it is shifted to Redshift, Amazon Redshift, the data warehouse. We have explored various solutions. When we copy or remove our data directly from any outside vendors, outside of warehouses and traditional storage, we firstly actually upload our data to S3 bucket, simple storage service. Then we can copy that data to Redshift or other form of data, which is quite simple and easy to manage. So this is another case how Redshift works. Uh, a person can log in with AWS console, check schema conversion tool, perform SQL operations based on SQL client, hosted on internet. The internet gateway goes to availability zone for RDS, Redshift, or data migration service. For example, if you are migrating your data from RDS for Oracle or for MySQL or for any other thing, you can migrate your data from RDS to Redshift using database migration service of the Amazon. It simply migrates your data. Or in the reverse process, you can migrate your data from Redshift to RDS or other form of database. AWS Redshift for retrieval and collaboration, we can use it for retrieval and collaboration also because it is fast, fully managed, petabyte scaled, making it simple and cost effective to efficiently analyze all your data using your existing BI tools. It is simple. You can also generate custom reports, uh, do analysis work using any form of analysis tools available on cloud. This is simple architecture of Redshift Spectrum. A person using any business intelligence tool could log in or could enter the could uh, create a request using JDBC or DBC bridge from client application, goes to the leader node. The leader node uh, controls or divide the task to other nodes. The other nodes goes to independent scaling the spectrums. They perform certain tasks, and the task is reflected to S3, and from S3 it is again fetched back, and it is done. Where we use redshift scaling and independent scaling. We could skip independent scaling stage or perform directly redshift scaling. We can scale up our data. So try creating your own data warehouse solution with Redshift just for fun. Or if you are building an advanced application, you can build a solution based on this.
Now we're going to create an instance for Amazon Redshift, that is data warehouse service on Amazon Cloud. You can navigate through the services option available and choose from the database the Redshift. Here you have various options. You can create a cluster, which is a fully managed cloud data warehouse service. The Redshift Spectrum extends the power of Redshift query to unstructured data on S3. You can work without loading the data into Redshift. You can create an instance, the launch cluster. You have to select the node type, number of compute nodes, cluster identifier, master username, and stuff like that. You have to provide a username and password. Uh, Choose from the database port, any virtual port like 8080 and more. You can select from any available IAM role. If it is not available, you can create a new IAM role. Then you have to associate a role with this and you can launch your cluster based on your requirement. After hitting this button, launch cluster, the cluster is being created, which may take some time to launch. The status is showing the creating and it will be completed in a few moments. It is based on certain region on Amazon Cloud and you can have various configurations available with you in the configuration console. Here you can create inventory of your AWS resources and manage them. The details are available here as the cluster status, cluster properties, cluster database properties, the backup audit and logging details. You can modify cluster, resize the cluster as per your requirement, delete or create a backup, IAM role. You can create a snapshot or complete copy replica of your database uh, and set a time for auto snapshot. For data, you can select all data or limited amount of data. You can set security permissions, the certifications, HSM connection. You can select the parameter groups. You can create cluster parameter groups. You can select a workload management based on parameters. You can select a find a reserved node. You can choose from events available, the subscriptions and more. You can connect various clients with different drivers, ODBC, JDBC driver, the native Java driver, and other drivers for different language support. You can install the different client tools, use configuration for particular cluster, and so on. And you can always check what is a new update in this Redshift or other services in a similar fashion. You can manage these things and it could be simply related or integrated with other services on Amazon Cloud as well. You could use credentials and most important the ARN for this thing. You have documentations available as well.